So let us discuss what are paths in directed graphs and also simple paths, circuits in a directed graphs. And we are going to define the directed graphs as a strongly connected and weakly connected. So I hope in undirected graphs we have seen what a path is. A path of length n we have defined, right? So it's nothing but, suppose from A to B, if you can travel by 3 edges, then we say it is a path of length 3. We say it is a simple path if edges are not repeated, and also we say it is a circuit if it starts at the same point and ends at the same point. The starting and ending points of the circuit must be same. So now if you take a directed graph, right? So you take a directed graph, we say A to B there is a path of length n if you find n edges, n directed edges, which drives you from A to B. Okay, so the direction is very important. For example, here you take this directed graph. Okay, let me take the second directed graph. This is H. So I'm taking this directed graph. Here, do you have a way from A to B? Or let me simply draw here. For example, you have 3 vertices like this, and we have 3 edges between these vertices. 1 is here, 2 is here, and 3. Okay, now the direction, this is how I'm taking. 1, 2, 3. Okay, so now my question is, let me make a small change. So 1, 2, 3. Do we have a path from 3 to 2 here? 3 to 2. No, there is no path from 3 to 2. Why? Because if you look at the edges, let me name these edges as E1, E2, E3. So edge 1, it is starting at 1 and ending at 2. And E2 starting at 2 and ending at 3. When it comes to E3, it is starting at 1 and ending at 3. Okay, so now I cannot go from 3 to 2 in any way. For example, if you start at 2, you can't move anywhere, because from 3 there is no edge adjoined from 3. Okay, so there is only in degree to 3. There is no out degree. From 3 you cannot move any point. Okay, whereas if you take 1, from 1 I can move to any point. From 1 there is a path to 2. So 1 to 2 there is a path of length 1. Okay, and similarly from 1 to 3 there is a path of length 1. But when it comes to 1 to 1, there is no path. 1 to 1 there is no path. Okay, so this is what we mean by a path in a directed graph. Alright, so even though we have edge between 2 vertices, we need to look at its direction. The direction is important here when it comes to directed path. So the same definitions you can take, whatever we defined it in undirected graph, a path of length n. So making sure of the direction of the edge, we need to take the definition. So path of length n and simple path, a circuit. All 1, 2, 3 we have 2 paths. So 1, 2, 3. Yeah, 1, 2, 3. Yes. 1, 2, 2 and 2, 2, 3. Okay. How 2 paths? Okay, 1 to 2 is one path. That's fine. All right. So 1, 2, 3, and another one is 1, 2, 3 directly. Yes. So yeah, there are 2 paths from 1 to 3. but one is of 2 length, another one is of 1 length. Both are not of same length. Now let me define, when do we say a directed graph is strongly connected? We say that a digraph is strongly connected. There is a path between any two vertices. Okay, if there is a path between any two vertices, then we say that the digraph is strongly connected. Okay, in both ways, not only in one way. From A to B, for example, you take some arbitrary points. Let's say U and V are two vertices of the graph. Okay, there must exist a path from U to V and V to U also. So then we say that the graph is strongly connected. Now let us look at this graph. Let me maximize it. Okay, now I hope you can see it better. So how about the first graph G? Is it strongly connected or not? From one point to any point, we must find a path. Okay, for example, so let me just make sure of a path from B to A, because from A to B you can directly see it. There is a direct edge, a path of length 1. But from B to A, how will you come? So we can see that initially you can start at B and you can come to D and then to E, next to A and then to B. Yeah. Okay, we need from B to A only. Okay, I can stop it here. Okay, from B to A we have a path. Similarly, you take any 2 points here in the first graph. We can find a path. For example, A to C, okay, there is a direct graph, and C to A, you can go this way. Alright, so therefore we can say that this graph is strongly connected. So this is strongly connected. Okay, so how about the second graph H? Is it strongly connected? Now I am looking at a path from A to B, but you can look at just A. A is just working as a receiver. There are only in degree vertices. There are no out degree vertices at A. I mean out degree edges at A. All right, no edges leaving A. All edges are coming towards A only. So if you stand at A, we can't move to any point, right? But however, whatever edges we have here in the first graph, the similar edges we have, but except the direction. If you forgot about the direction, if I just concentrate on the edges, so the edges are here and here are same if you forget about direction. Okay, now without, if we do not have this direction, we can start at any point and we can move to any point in this graph. Okay, underlying undirected graph. Underlying undirected graph, I mean just remove the directions from the edges, that's it. So the underlying undirected graph for this picture is this. So this is the underlying undirected graph of H. Okay, how about this? Is it strongly connected? Is this graph strongly connected? Yes, this is strongly connected. Why? Because between any 2 points we can have a path, because there is no restriction on direction here. Okay, since the underlying undirected graph is strongly connected or connected, I mean, remember one thing, strongly connected and connected both are not same. I hope in the case of undirected graph it is same, right? Yeah, in the case of undirected graph, connected and strongly connected both are same. But if there is direction, they are not same. In directed graph, it is not. All right. So you can see that I can simply say underlying undirected graph is, if it is connected, then the digraph is weakly connected. Okay, now this is weakly connected. The original digraph is not connected, but the underlying graph is connected. Do you understand? Connected, I mean, I'm talking in terms of direction edges. So having path from one vertices to any vertex. That is what I mean. So let's look at one more example. Suppose if I take this graph. So is this connected? I mean, is it strongly connected? So the answer is no. Yeah. But is it weakly connected? Yes. Oh, some are saying no. Why? Why is it no? Because if you look at the underlying undirected graph, that is connected, no? The underlying undirected graph is connected. It means you can move from one edge, one vertex to any vertex. For example, here to here, you can move it like this. First, you can travel along this edge and then this edge. Give an example that one direct graph strongly connected and the other one connected. No, what is it? One directed graph is strongly connected and the other one is connected one. I didn't understand the question. Strongly connected one we have seen. You can see an example of strongly connected graph. This one, the first graph. Okay, or you can take now this is strongly connected from one point to any point. Strongly connected and connected both are not same. Okay, strongly connect. Okay, fine. Understand. Okay, this is strongly connected. This is strongly connected. Okay, now let us look at the graph, which is connected but not strongly connected. So now if you observe that this graph is connected. I mean, there is an edge between any two vertices. If we do not take the direction into the picture, directed graph neither strong or weakly connected. And the digraph direction matters. There are only two types we can have actually here. Connected, I mean, that is weakly connected. So this one is, see, if a graph is connected, that becomes weakly connected. Let's say you forget the direction of the edges. Okay. Now I can say that is weakly connected. Okay, here let us do one thing without confusion. Let me do not use the word connected graphs when it comes to directed digraphs. Okay, let me say that either is it strongly connected or weakly connected. Weakly connected one, I am saying connected. That's what my intention. Okay, so let's stick to only two things in digraph: strongly connected and weakly connected. Weakly connected, it means underlying undirected graph is connected. So is it clear now? Yeah. So in digraph, I am just saying there are only two types. One is strongly connected. Strongly connected, it means from a vertex to any vertex, there is a path, there is a directed path. Okay. So that is what a strongly connected graph is. Now the other category, it looks connected if you remove the directions, because you may not find a directed path from A to B, but you will have just a set of edges which can connect from A to B. It means underlying undirected graph is connected. That is what weakly connected. Okay, so let me do not use the word connected here in the digraphs. Only two categories: strongly connected or weakly connected. That's it. Yeah, is it clear, or should I go with one more example? Okay, when we say that digraph is disconnected, if it do not fall into these two cases, yeah, that's a good question. So when do you say that a digraph is disconnected? Okay, so if it is neither strongly connected nor weakly connected, that's what we call disconnected graph. Now in the undirected graphs, we define the connected components. Okay, there we define connected components. What is it? That is a subgraph, I mean a connected subgraph of the given graph, which is not a subgraph of any other, I mean which is not a proper subgraph of any other connected graph. Okay, so that is a definition of connected component. Maybe definition may be complicated, but you can easily understand by looking at the picture, right? So here let us define a strongly connected components. So what do you mean by a strongly connected component? I hope you can tell me the definition. So in a strongly connected graph, the strongly connected component is that graph itself. Okay. So we are talking about disconnected or a graph which is not strongly connected. So let me do one thing. Let me take a graph, the digraph in which we can find the path between any two vertices in the graph. It is called strongly connected graph. So in digraph path, it means the direction also matters. Okay. So now let us look at a digraph which is not strongly connected. Okay, maybe instead of drawing, can I? Yeah, I hope I can take this picture. So it is very clear that this entire graph is not strongly connected. Okay, but it is weakly connected. But in this, do we have any strongly connected component? Yes, we have. That is B, C, D. So if you look at this component is strongly connected. Maximal strongly connected subgraph. Okay, and let me take one more directed graph. Yeah. So do you have any strongly connected component here in this graph? But there is no line in which is in two directions, no? If you say, I mean, a graph between two vertices is strongly connected, you must have these two edges. This is strongly connected. Okay, whereas when if you take just this one, this is not strongly connected. That is weakly connected. All right. So there, max you can take just one vertex. That's it. You can take a single vertex. That's it. All right. Okay. Now let us discuss about this graph. Is it strongly connected or weakly connected? Find if it is not strongly connected, try to find strongly connected components. So is it strongly connected? What is okay? Then give me a path from C to D. Is there a path from C to D? No, there is no path from C to D, right? So it is not strongly connected. It's very clear that it's not strongly connected, but it is weakly connected. This one is weakly connected. But however, I'd like to know what is a strongly connected component here. Do we have any strongly connected component? I hope I found one. ABE. Okay, by looking at this picture, I got one idea. Let me draw another graph. All right. So now the graph, this is here. I mean, it has 6 vertices. Okay. So this graph is not strongly connected. Why? Because you cannot establish a path from this vertex to this vertex, a directed path. Whereas this graph is weakly connected, right? Now, what is strongly connected component in it? How many vertices it has? The strongly connected component. Square with diagonal. Yeah, again, this is also important. Right. So I can't take just this one. I can't take just this one. All right. This is a subgraph of this graph. Okay. Now this is a strongly connected graph. This itself is a strongly connected graph. Even though this is strongly connected, what happens is this guy is a subgraph of this one. Okay, but when you say strongly connected component, we must look at the maximum possible guy. All right. So you're not allowed to just to take this expression, right? You need to consider the diagonal also. Okay, and we can't say that the triangle, just the triangle. What is it? Yeah. You're not allowed to take just the triangle because this is also a subgraph of this one. Okay, so we must take maximum connected subgraph of the original graph. Okay, so this one is the strongly connected component. All right. So there is a theorem about undirected graphs. In a connected undirected graph, there is a simple path between every pair of vertices. I hope that is easy to establish, right? I'm talking about undirected graph. In a connected undirected graph, there is a simple path between every pair of vertices. So we can take help of these paths to know whether two graphs are isomorphic or not. Okay. So if you have two directed graphs which are isomorphic. So if two graphs are isomorphic, let's say if you have a simple path of length 2 in one graph and the other graph also you must have. Okay, suppose if you have a simple circuit of length k, in the other subgraph also, I mean in the other graph also we must have a simple circuit of length k. Suppose in one graph you have a circuit of length k, but in another graph you do not have, then they are not going to be isomorphic. So there is one example here. So here you are given with two graphs, you are asked to find whether they are isomorphic or not. You can see that the number of vertices are same here, number of edges are same, even the degree sequences are same. Even you can look at neighbors of or adjacent vertices of each vertex when with comparing to degree, you can see that they'll have the similar properties. Okay, so in this sense we can't tell. So let us try to investigate in terms of path, right? So you look at the second graph, there is a simple path, simple circuit of length 3, that is x, y and z. So this is the circuit of length 3. Of course there is one more circuit of length 3, that is u, v and w. Okay, now let me look at the first graph. Do we have any circuit of length 3 here? So if you look at the circuits, that can be A, B, yeah, and then D, then you must come back to C and then A. So you have a circuit of length 4, and similarly you can find one more circuit of length 4, and another circuit is the total graph itself. Yeah, we can have one more also. But you look, we do not have any circuit of length 3. Okay, so it is very clear that G1 do not have a circuit of length. Alright, but when it comes to G2, so G2 have a circuit of length 3. So therefore the conclusion is that G1 is not isomorphic to G2. Okay, suppose here all these three properties are matched. So now if you try to go for an isomorphism, you do not get it. Even you can directly find while changing the edges. You may think like this: what if I keep C here and E here? If I interchange these two, you may get this picture. No, are you going to get this picture if you interchange those two? Someone is saying yes. Okay, then let me try. Let me show you. Just by interchanging C and E, let me show you what is the picture you are going to get. So B, D. Now here I'll take C, and here I'll take uh, E here and C here. The bad thing is I'm writing both alike. So this is E. So this is E. Alright. So now let me write the edges. How about A and F? Do I need to change or no need? So if I assume this is A, what is it? If I assume this is A, they are connected. And this one is F. Right. So these two are connected. These two are connected. Until here it is fine. Okay. Now you can establish these two. But here comes the problem. What the problem is? E is adjacent to F. C is not adjacent to F, if you observe. Okay. And A is adjacent to C. So we do not get the same picture as this. Okay, there is a chance of getting confusion here. You may think that you can simply change these vertices, therefore these two are isomorphic. So we have to be careful. Okay, we need to take care of A and F also. One side there is no problem, fine, but the other side you'll have this kind of picture. At max, if you want to separate without intersection, what you can do is, Let me try to draw it directly. I don't think so. I can go without intersection. No chance. Somewhere, at least one line intersection happened. Without intersecting the edges, I'd like to draw the graph. Oh, no, no. It is possible here. It is possible. Oh, it is possible. This way it is possible. I mean, this is A, okay, and this is B, and this is E, and this is F, and this is D, and it is C. I can separate it like this. But however, so this is C to E, C to, oh, C to E. Okay, in the earlier case, I did not write that edge C to E. Oh, here I missed to write it. Now, now, now what else I can do not to have intersection? So here that I forgot to write this edge. Not possible. Anyway, you think about it. So there is one more example. Instead of drawing, let me simply cut it. So given two graphs, are these isomorphic? So if you see in terms of number of vertices, number of edges, when degree sequence, all will match. And how about circuits? Here is a circuit of length 3 and here is circuit of length 4. How about in the first graph? Yeah, there is a circuit of length 3, that is U1, U3, U4, and circuit of length 4. What is the circuit of length 4? Yeah, I can see it. U1, U3, U2, U4, U1. I mean, this and next this, this, this. U1, U3, and U3 to U2, U2 to U5, and U5 to U1. So this is a circuit of length 4 in the first graph. So we have circuit of length 3, length 4, and here we have a circuit of length 5. How about in the first graph? Do we have a circuit of length 5? So in the second graph, it is outer part only. You can easily see that. Starting at V1, coming back to V1. How about here? Starting at U1, U1 you can go to U3. Oh, okay, instead of going to U3, you just go to U4 and then you follow this direction. U3, U2, U5 and U1. Now we have a circuit of length 5. So now almost all properties are agreeing, right? Now it is reasonable to look for isomorphism. So what is the isomorphism we can have? I hope you can bring U1 to here. It's like you bring U1 to here and you take this triangle out. Then I hope you will get it. I mean, you rearrange the vertices like this. U2, U5, you keep it like that, and now you bring U1 here. Instead of keeping U1 there, you bring it down, right? And then you write U4 here and U3. Am I going to get the picture? U1 to U5, U5 to U1, and U5 to U4. Oh, there is no. Oh, U1 to U4 is there, and U4 to U3 is there, and this one. And there is one more U5 5 to U2. What I'm missing? Yeah, U1 to U3. I hope we got it. Okay, so now we can define an isomorphism. So what is isomorphism here? So this one is V2. So this you map it to V2, and U1 map it to V3, and this you map it to V1, and U2 you map it to V5, and this you map it to V4. Alright, so that is the isomorphism. Therefore, here isomorphism from V1 to V2, so that is defined like this: f of U1 is mapped to V3, and U2 is mapped to V5, and how about U3, U4 and U5? Three went to 1 and 4 went to 2, 5, 4. So I hope we can find the same adjacency matrix. Now you do one thing, just write adjacency matrix for G1 in this order. The order is U1, U2, U3, U4, U5. You mention that adjacency matrix in this order AG that equal to adjacency matrix of H AH that equal to, you can write, I mean, how do you write adjacency matrix of AH? That order we need to mention. So you write that adjacency matrix, and here for the second one H, the order of the adjacency matrix is this. What is it? V3, V5, V1, V2, V4. So what is AZ? I hope we can easily write. What is AG? So that is 0, 0, 1, 1, 1. And next one, U2 is incident with only two vertices, that is 3 and 5. And how about U3 is incident with 1, 2, 4. So now I need to, this is anyway 0, there are no loops. Is there a connection between 4 and 5? No. Similarly, you can see that this is same as adjacency matrix of H in this order. So you can see that V3 here is connected with V2 and V4 and V1. So in the first column of AH, you will get 0. It's not connected with V5, whereas it is connected with, oh my god, V3 is connected with V2. Yeah, it's connected with V1. So since it is connected with V1, you get this. So similarly, you can see that the other columns are also same. So it is very clear that G is isomorphic to H. Okay. So now let me go to some exercise problems. So let us discuss this problem. Use paths either to show that these graphs are not isomorphic or to find an isomorphism between these graphs. Now this we already discussed. These two are not isomorphic. Do you remember? So now using circuits, how do we say? I hope I can see a circuit of length 4 here in the first graph. So in the first graph, we can see a circuit of length 4 in G. But how about in H? Do we have a circuit of length 4 in H? No, we have. But the thing is, this circuit is created with the help of vertices of degree 3. But this circuit, 2 vertices are of degree 3 and 2 vertices of degree 2. Okay, you're saying number of vertices of circuits of length 4 are not same. Okay, let me count the number of circuits of length 4. So this is one circuit, and another circuit of length 4 is this, the middle one. Any other circuit in the first graph of length 4? Outer one, okay. So 1, 2, 3, fine. So how about in this picture? So this is 1, and also you can say that outer one is 1, fine. So even if you look at the circuits here, how the circuit is created, like if you look at the vertices and you see their degrees, okay. If a circuit is created of length 4, let's say where each vertex is of degree 2, let's assume. Then in the other graph also you must have a circuit of length 4 so that each vertex is of degree 2. So that also matters. Okay, so here if I mention the degrees of the vertices, in the original graph this is a 3 degree vertex, and this is 3 degree, and this is 3 degree, this is 3 degree. Okay, but when it comes to here, this is 3 degree, 3 degree, 2 degree, 2 degree. The same thing here, 3 degree, 2, 2, 3. But how about the degrees of this one? 3, 3, 2, 2. Okay, this is fine. Outer, but again there is a problem. The degrees, it's like 3 is connected to, 2 is connected to both 3 degree terms here. But here 3 is connected to 1 third degree and 1 second degree. Alright. But anyway, yeah, you can see in terms of number of circuits here and there, or we can speak in terms of the degrees of the vertices of the circuits in the from the original graph. Alright. So here we have a circuit which is given by a vertex each of degree 3. But here we cannot find a circuit which is given by a circuit of vertex of degree 3. Suppose if I take vertex, all vertexes of degree 3, what is it? Do we get a circuit? V1, V5, and then V7, V3. We don't get a circuit. We get two connected components. This is a subgraph with two connected components. Okay. Alright. So to say that it is not an isomorphism, you can tell n number of reasons here. But however, they are asking us to show it using paths. Yeah. You can take these circuits. Alright. Circuit is also a path, but which is a closed path. So there is a question. Find the number of paths of length n between two different vertices in K4. So what is the adjacency matrix of K4? The adjacency matrix of K4, you know there will be 4 vertices, right? Except the diagonal elements, the rest elements will be filled with ones. So this is the adjacency matrix of K4. Alright. So now they are asking about number of paths of length n between any two different vertices. Okay, for that we need to see what is a square of K4, that is product of these two. So what is the product? So if you look at the first column of the result of the product, that is sum of last 3 columns. So 3, 2, 3, 2, 2, 2. So the next one, it is a sum of first, third and fourth. So 2, 3, 2, 2. I hope next you can easily tell me that's what 2, 2, 3, 2. Am I correct? Because it is sum of 1, 2, 4 columns. Alright, and the next one is 2, 2, 2, 2. Alright. So find the number of paths of length n between any two different vertices of in K4 if n is 2. Okay. How many paths are there? How many paths of length are there? Length 2. Yeah, last one is 3. This is 3. So the question is about two different vertices. They are not asking about the same vertices. If they include same vertices, then I need to consider the diagonal elements. Okay. So since they are asking about different vertices, so you just look at non-diagonal entries. So the answer to this question, when it is 2, there are 2 paths. If you take any two different vertices, there are 2 paths of length 2 in K4. Because you can see that from 1 to 2, there is a path of length 2. From 1 to 3, there is a path of length 2. From 1 to 4, there is a path of length 2. Like that, we can describe. So now they are asking about a path of length 4. Oh. Now I need to multiply a square 2 times. A square into a square. So now we need to write a power 4, right? I hope for that I need to know what is a square. So let me copy. So this is a square. Okay, now let me find what is a power 4. I hope writing one row I can write the rest of the rows, or writing one column we can write rest of the columns. Alright. So now the first column of the resultant matrix, first column you multiply with 3, rest of the columns you multiply with 2 and you add it, right? So it is when I multiply with 3, first column it's 9 plus 4 plus 4 plus 4, right? 12, so 21. So next, now when it comes to this, the second one, that is 6, 6, 2, sorry, 4, 4, right? 20. Alright. So the rest you can easily write 20, 20. 20, 20 is over, right? 21, 20, 20. I hope we are done. Okay, so now answer here is between any two vertices, any two different vertices. So there is, there are 20 paths of length 4. There are 20 paths of length 4. And then next they are asking about 5, a power 5. So to calculate a power 5, I hope I need a power 4 and also a. So let me just see what is a. A is here. So now a power 5. So what is a power 5? So a power 5 equal to, now it is sum of the last 3 columns, because we have 0 here, 1, 1, 1 here. So that is 20, 20, 20, 60, and the next one is 61, 61, 61. I hope you know the rest. Okay, so what is the answer? Between any two different vertices, there are 61 paths of length 4. Sorry, length 5. Okay, so like that you can think about any power. So I hope it is clear. So find the number of paths of length n between any two adjacent vertices in K3, 3. Same. What do you do? You know what is K3, 3 is, right? But there are 6 vertices. You will get 6 by 6 matrix. But so this one is K3, 3, right? Now what is the adjacent matrix of K3, 3? If I name this as 1, 2, 3, 4, 5 and 6. Yeah. So we'll get 0 here. So 1 is connected to 4, 5, 6. And 2 is connected to 4, 5, 6. And similarly 3 is connected to, we didn't see the matrix of an complete bipartite graph, right? So yeah, it looks beautiful. It's like there are four components in this matrix. So 0 matrix, 0 matrix, 1 matrix. Anyway, so now what is the question? Number of paths of length n between any two adjacent vertices in K3, 3. So when k is 2, let's see, when n is 2, length is 2, it means we need to think about a square, right? So what would be a square if a looks in that form? So the first column of the resultant matrix is the sum of last 3 columns. Okay, so you can easily say this is 3, 3, 0, 0, 0. So you'll have the same copies. Right. Now, when it comes to the other one, it is sum of the first 3 columns. So that is 0, 0, 0, 3, 3, 3. Similarly, the rest you can fill it easily. Therefore, number of paths of length 2, number of paths of length 2 between between two vertices of a complete graph, complete bipartite graph, there are 3. So now we need to think about length 4. Okay, so this we need to multiply. A square needs to be multiplied with a square. So when you take a power 4, what do we get? A power 4 we get 9 plus 9, 9 plus 9 plus 9, right? So that's what you'll get, 27. In a power 4, you'll get 27. And whereas in a power 5, that is 27 plus 27 plus 27. Okay, I hope we can see 81. Okay, so similarly, you think about remaining problems also.